Hi everyone. Today we are diving into how we built and improved a classifier for a loan approval system. I'll walk you through the steps I took, including feature engineering, model comparisons, hyperparameter tuning, and validation strategies. So the first thing we need to talk about is improving the performance of classifiers. To start, I applied a few feature engineering techniques, which is key to model being smarter by creating transformed features that can help better predictions. So in this case, I transformed categorical values and um, numerical values, and I also created new features by combining existing ones to capture more complex patterns. For example, I created an interaction term between a customer's income and the loan amount to better capture risk. Um, the techniques improve prediction quality because they help the model focus on relevant patterns and ensure that it doesn't get misled by irrelevant and or out of scale features. Now let's talk about the models that I compared. I tried three different classifiers, the XGBoost, PyCaret, and a neural network. So first of all, the XGBoost is a baseline model. It's easier to interpret and faster to train and performs reasonably well. How However, it is sensitive to feature scaling and doesn't handle nonlinear relationships very well. And next, I also tried the I also tried random forest. And it combined multiple decision trees to make more robust predictions. It does a better job, but it's a bit slower to train and might overfit with a large number of trees, which can make it less interpretable. And finally, we also looked at a neural network model, but this model is not a very good fit for our data. So speaking of, speaking of our original data, we noticed that the data is severely imbalanced. So in the loan approval context, one common problem is that loan defaults are much less frequent than approvals, which can lead to the imbalanced data set. To handle this, I used SMOTE, which stands for Synthetic Minority Oversampling Technique. It works by creating synthetic samples for the minority class, ensuring that the model has enough data to learn from when making predictions for defaults. This helped boost the recall of the minority class without sacrificing too much precision, leading to a more balanced F1 score. Um, Next, let's talk about hyperparameter tuning. I tuned the hyperparameters of my models using grid search cross-validation. This helped me find the best combination of parameters for the XG model. I tuned for XG boost, I tuned parameters like learning rate, max depth, and the number of trees. I compared performance before and after tuning, and there's a noticeable improvement in both precision and recall. Uh, Hyperparameter tuning is essential because it helps the model find the optimal setting to maximize its performance.
So when it comes to validations, I use the k-fold cross validations. When I split the data into k subset for each float, the model was trained on K1 subset and the test on the remaining subset. So this helped me to elevate to the model performance on different population of the data, providing the better elimination of the generalizability. This approach helps to reduce the variance in model invalidation, compare the simple train test speed, and ensure that we aren't unfitting and one specific subset of the data. So to assess whether my model was underfitting or overfitting, I create the learning curve by plotting training and the validation error rates over increased amount of training data. So in this case, the curve should have add more data, and the model's performance is stable. So this suggests that my model is never overfitting or underfitting, but I continue to monitor its performance to ensure stability. And next, I use the confuse matrix to elevate to trade-off between false position and the false negative. In the non-approved context, the false positive means we approve the norm for someone who will default, and the false negative means we reject a norm from the creditworthy application. The precision recall curve are also useful, especially when dealing with the imbalanced dataset. By adjusting the decision threshold, I could optimize of the trade-off between precision and recall, depending on the weather and business prefer minimizing risk, like the false position, or ensuring more loan approved, like the false negatives. So about the future improvement, we did I have more time to resources, so I look for the external datasets to further improve the model predictive accuracy. For example, the macroeconomic trends like the unemployment rates or credit data on the application histories. So could help provide the in the addi- additional content for the making better predictions. So I also implement the strategy for the monitor model performance to production. This includes the setting up the audit for the data draft. So when the distribution of the incoming data starts changing, and regularly retraining the model to keep it up to the data with the new patterns. So this case we covered a lot of ground today. So from the future engineering and the model comparison to handle class imbalance and the way data model performance. So by applying this technique, we build the non-approved classifier and the balance performance and the business impact. So thanks for tuning in. If you found this video helpful, make sure to subs data to insight. 最后一句怎么是关注？